Hi, welcome to this new lecture on specifically pulsing modes and some aspects of instrument design associated to the way we pulse the field evaporation in atom probe tomography. Again, I can only encourage you to go back to some of the main textbooks, especially in that case, the one on the local electrode atom probe from Larsen et al. And some also aspects of the laser pulsing and everything are quite well covered in the book from the French people, William Lefebvre and François Vurpillot, and we try to cover most of these aspects too in our book with Mike Moody and Jolie, but it starts to be a bit dated now. Going back to how atom probe works, so we have this sharp needle, low temperature, 80K, we apply the voltage, the atoms on the surface are going to transition into ions under the influence of the high electric field, and then they are projected away following trajectories that are determined by the distribution of the electrostatic potential, going through the counter electrode, being collected by a position sensitive detector. And here comes the point of interest to this particular lecture, which is the pulsing mode. So either we can use high voltage pulses or laser pulses to either temporarily increase the field or increase the temperature to cause or trigger the departure of the ions. And this gives us the starting point of the time of flight measurements, and we can deduce the mass to charge ratio of each of the ions detected based on their time of flight. And all of this, through a bit of magic, we turn in this three-dimensional point cloud, showing each point being one ion that was identified and reconstructed. So yes, we want the mass spectrum and we want the 3D reconstruction. This is what we want from an atom probe dataset. How to get there and what mode should we get or to use, voltage pulsing or laser pulsing to get to that data can be a matter of choice, and we want to try and help you guide this decision through this lecture. Effectively, if I go back to the basics of field evaporation, which is the topic of a separate lecture, I look at the electric field I need for a certain temperature. I'm going to have a curve here corresponding to a certain rate at which I'm going to field evaporate the atoms. So typically I will choose a base temperature and a certain DC field at which I'm going to hold my specimen, and if things are right, I'm going to have zero field evaporation unless I start pulsing either through high voltage, so I'm increasing the field temporarily, or through laser pulsing, and then I'm increasing the temperature temporarily. And again, there's a whole range of different curves like this. As I increase the detection rate or field evaporation rate, it forms a network of these curves. If things go well and I'm not field evaporating at the base temperature or the base field, I'm detecting nothing in between pulses, and what I get is coming from the specimen in between pulses, and what I get is well-defined series of peaks in the mass spectrum and a low level of background, mostly coming from the dark current of the detector and some ionization of residual gases from the at the DC voltage. So we can either pulse with high voltage pulsing, and this has a number of idiosyncrasies which I'm going to discuss briefly, and this has led to the integration of reflectron lenses in the design of atom probes, and I'm going to briefly touch on the motivations and how this functions. Going back to the way that we are actually functioning in some ways, so we have this DC field, right? And then when I apply a high voltage pulse, I'm temporarily increasing the field. The field evaporation process is probabilistic, so I'm increasing the probability that an atom will be subject to enough field that it will be field evaporated. And so there is if I look at the rate, the probability of evaporation will be maximum during the pulse. It will just go from nearly zero, or zero in an ideal case, to something that is measurable, where I'm starting to detect a number of ions. The width of this probability function is not zero. It's not instantaneous, basically. So there will be a distribution in the range of acquired energies, because if not all of the ions are emitted right at the top of the pulse, but slightly below the top of the pulse, less energy will be accessible to the ion for acceleration, which will lead to a distribution in the kinetic energies and hence in the times of flight of the ions. So if I go back to this probability distribution, so that's the pulse, that's in log scale, it's a bit cheeky, and that's the probability of field evaporation. This means that if not all of the ions are emitted at the top of the pulse, the ions are accelerated through a time-varying electric field, and some of the energy might not be, that was in principle available, will not be provided to the ion. So there's a spread in the kinetic energy. And if I go back to this old paper by Cerezo, for example, I can see that this leads to this spread in energy means that some ions are slower, so their times of flights are longer, their mass to charge will be assumed to be higher, and this leads to these tails in the mass to charge spectrum that you can see there. This widening of the peaks is hence related to some level of kinetic energy that was not acquired. And these tails can actually prevent us sometimes from detecting some of the peaks, the minor peaks, and this is why we might want to maximize the mass resolution, the width of the peaks. How can we do this? A way to increase the mass resolution is to use a so-called reflectron. A reflectron is basically a mirror, an electrostatic mirror. So what we can do is that the ions will fly and enter a region where there is an electric field that is of opposite direction and of magnitude slightly higher than the magnitude of the field that projected the ions away from the specimen, in a way that the ions will go inside of this reflectron, be stopped and reaccelerated back. And there's a whole range of equations and voltages that we can apply, but basically what that means is that an ion that comes in with more kinetic energy will fly deeper into the reflectron before being returned, whereas an ion with less energy will be stopped earlier and be returned. Ultimately, the time of flight of the ion between the specimen and the detector will be the same, which means that the mass resolution will be improved. So if I look back at this first implementation of a reflectron on an atom probe by Cerezo, this is a typical mass spectrum for an iron chromium alloy. And if I take more or less the same specimen, the same material, but through the reflectron, I can see that these long tails that I was seeing in this spectra have been pushed back into the main peak. And so now I can see peaks that are well separated. And that improves the mass resolution, that improves the chemical sensitivity and accuracy of our compositional measurements. This was all done with a reflectron that I've shown here, something with a small angle of admission. But there are a number of issues associated to reflectrons, in part due to the fact that the grid will cause the loss of a number of ions, and also the trajectories of the ions is really not that straightforward, and the way it's processed in the commercial instruments is not always completely straightforward. And I will get back to this later in the following. But basically, we need to apply a correction to the times of flight and to the trajectories that is really not straightforward. So if I look back at the way this was described early on by Kameka, the assumption is that there is a point source and you can calculate all of these trajectories and position the detector at a certain angle and a certain distance so that all of the ions will actually emitted from a certain mass to charge will all end up with the same time of flight to reach that position. Here, the correction in the y-axis or the x-axis will not be the same because the ions in one direction will be returned and in the other one it's just not as vastly affected. So we need to assume typically these differences in the compression of the trajectories and in the times of flight that need to be corrected slightly differently. And if I look at the detector map that I would get for a pure aluminum dataset acquired here, for example, on a machine with a reflectron before the correction and after the correction, I can see here a number of distortions that have been introduced. And in principle, they get corrected by the application of these distortion maps. But we always use the same map for all the samples, and there might be subtleties that are involved in the projection of the ions, and especially as the specimen evolves in size, we might end up with small distortions still introduced by the reflectron. And this is not corrected whatsoever. So there's a loss of spatial resolution associated to the use of the reflectron. But we gain in mass resolution, so it's always a bit of a balance to be found. The other way to pulse is to use laser pulsing and hence to increase the temperature for a short amount of time. So how does that work? If I take a sharp needle and I send a laser pulse, again the probability of field evaporation will be increased if I increase the temperature. So what I can do is just heat the specimen locally at the apex and with a short pulse, and then the temperature of the specimen will increase, and then because this is hot and this is cold, the heat will be conducted away, so the temperature will progressively drop over time. The thing is, what we're looking at is typically a specimen with dimensions that are very small compared to the wavelength of the illuminating wave. So the interactions between the laser pulse and the specimen are again rather complex. So back about 15 years ago, we started looking into this when we implemented short laser pulses onto sources, onto atom probes. And for example, we could see that depending on the change of the angle between the specimen main axis and the polarization of the light, the voltage that we would need to provoke field evaporation at a certain rate was varying. And it was varying differently for different samples, and it was varying differently for different laser pulse energies. There was also quite a lot of work done about 10 years ago by the group in Rouen on the influence of the wavelength, for example, and they performed quite advanced simulations of the absorption of a sharp needle. And you can see here that there will be hotspots of absorption separated roughly by a wavelength. And this is just due to the way an electromagnetic wave is going to interact with a metallic object. So there will be these hotspots of absorption that are localized on one side of the specimen. So it doesn't necessarily cross the entire specimen. And what they showed is that there was basically a peak of absorption of the light at a distance that was more or less a wavelength away from the apex. So the shorter the wavelength, the more localized is the absorption at the top of the needle and at the tip of the needle. And so there was a move from early on, about 15 years ago, using infrared lasers, and now most of the commercial instruments are equipped with a UV laser. And this is in part because of this. Looking at actual measurements, you can see that at a short wavelength, at 320, for example, you get sharp peaks because the absorption is really well confined at the top of the needle, and so the cooling will be very fast. But if the absorption is mostly a micron down the shank, the heat needs to first travel up the shank and then back down. And so you end up with these peaks that have a long rising edge and a long decay. So the mass resolution will be very dependent on the way the light is absorbed by the specimen. Again, I invite you to read some of those papers, but this also then depends on the heat conductivity of the material. So for example, for aluminium that conducts heat very quickly or very well, the difference as a function of the wavelength is not that bad, because even if the absorption is down the shank, the heat will travel fast to the tip and then back. But if you take a piece of stainless steel that is not as good a heat conductor, it will take a long time for the heat to travel along the shank and back. So you're going to have a very strong dependence on the wavelength. If you look at these peaks, not all of them would be acceptable. And all of this would be dependent on the diffusivity, the heat diffusivity. And if you do some very simple finite element method simulations of the heat conduction, you will see that there is a very strong difference as a function of the heat conductivity, but also a difference between the different sides of the specimen. And I'll get back to this afterwards, but this is something to bear in mind. Sometimes we end up having specimens that won't be symmetrical anymore because of this. So let's move on to the big fight between high voltage pulses and laser pulsing. And this is something that you need to understand somehow to make an informed decision on what parameters you should use for acquiring data. So why did we bother using laser pulsing? High voltage pulsing was implemented early on atom probes. It worked okay, but high voltage pulsing has a number of challenges, and especially when you want to analyze brittle materials. So for example, when we want to look at multi-layer thin films, for example, when we apply the high voltage, when it translates into a high field, this also equates to a high electrostatic pressure. And this high electrostatic pressure, especially when it starts to be applied cyclically, during the pulsing, can make the sample very brittle and break early on. So the yield would drop massively. The mass resolution is maybe more limited because of this spread in the kinetic energy of the ions, and some of it can be recouped by using a reflectron, but this comes at the cost of the spatial resolution in parts. The main limitation for high voltage pulsing, and one of the key motivations to implement laser sources onto atom probes, was that if you want to transmit a high voltage pulse through a polyconductive material, the shape of the pulse will be completely deformed, and you end up with pulses that are odd, not always very intense, and so the analysis conditions would get potentially very bad. Laser pulsing was good, but it's not necessarily always, leading to the best performance. So sometimes we need to think a little bit about what we do. Effectively, it can be used on almost any material. It doesn't mean that we should analyze any material. Sometimes the mass resolution is really not very good, and it can be related to the specimen itself and its thermal conductivity and so on and so forth. There is always a degradation of the spatial performance because we are provoking the field evaporation triggering the field evaporation at a higher temperature. So we can activate more surface diffusion effects, and also it makes the field evaporation less critically dependent on the amplitude of the electrostatic field. There will be a dedicated lecture to this in the next few weeks, so just bear with me. And there are also issues because the performance of the technique might be very difficult to pinpoint. It might vary from specimen to specimen and even over the course of a single analysis. I'll give you a bit more details afterwards. And again, the higher temperature can trigger all sorts of different effects that might not be wanted. Looking at a series of analyses performed on a single specimen of pure aluminum, I can see that changing the laser pulse energy, in that case it was with the green laser, you can see that the map is changing quite significantly as a function of the laser pulse energy. This is related to the fact that at some stage the field evaporation takes place at a higher and higher and higher temperature, and this reflects changes in the specimen shape as we change the field evaporation temperature. This would not be accounted for in the reconstruction, so we would always assume a spherical cap, which in that case would be very far from the truth, because the fact that you can see here a very dense region on the detector means that this region comes very flat around the O2 pole, the set of planes, compared to this region here that is more or less homogeneous all across the field of view. So there are additional issues like this when it comes to laser pulsing that are not always considered. This was a simulation of the absorption of the laser light, for example, in a stainless steel specimen. And this is an image of the specimen after an interrupted analysis. And you can see that effectively there seems to be a hotspot of absorption right there on the side of the needle, and this might have actually changed the microstructure quite a bit. So it's not always 100% sure that we are not modifying the specimen when we are using laser pulsing. So let me give you an example. Two specimen geometries, one with a very small shank angle, then the heat that is generated at the apex here actually has a hard time traveling back because this entire region is hot. So this needs to cool down first, and the volume is fairly small. So you end up with very poor mass resolution and a very long time to go back to zero field evaporation. Whereas if we look at a specimen here down the shank, where the shank angle is bigger, the specimen is fatter in some ways. So the cool down time is much lower, and the mass resolution increases quite significantly. This also means that this evaporation time will depend on whether we have, as we go down the shank of the specimen, so during the analysis as we are analyzing the sample, the performance here might change quite a lot, and the mass resolution can be very bad at the top and much better at the bottom. So this is something that would never happen with high voltage pulsing. And again, the time there, to go back to zero will change quite a lot. So there are many variables when we're using laser pulsing that might not have a reason at all when we're using voltage pulsing. And sometimes the mass resolution might be what you need is this one and what you're getting is that one, and you don't really understand why. And why? It's because your specimen is too small or too big, and it's not always that easy to control when we're preparing specimens. Finally, an aspect of laser pulse evaporation that is not always straightforward to interpret. This is an analysis of gallium arsenide from Emmanuel Marquis, and we can see that there is a distribution in the size of the molecular ions that we are detecting, with smaller ones on one side and larger ones on the other, and this is because there is a range of temperature across the specimen surface. But as we start increasing the laser pulsing energy, this distribution changes, and we have these sort of weird gaps in the data that might actually just be coming from surface diffusion. And if we move to low evaporation pulse fraction in high voltage pulsing, We are field evaporating primarily from one side, and that's because here we have a sharper specimen on one side. This is the hot side, this is the cold side. And there's definitely some specimen shape changes happening as we go from one analysis condition to another. But it also translates into different compositional analysis. So after some time at low temperature and high voltage pulsing, we get a homogeneous field of view there, a density in the field of view, mostly small molecular ions. And this is a typical mass spectrum that we're getting in laser pulsing mode, quite sharp peaks. With voltage pulsing, we get very weird shapes of the peaks, but the composition is better. And in that case, we also get more homogeneous evaporation. We don't know necessarily why we have these weird shapes, but things will come in due time. But all of these indications tell us that it's not always straightforward that we should choose one set of analysis conditions. And pulsing with laser or voltage can be dictated by the performance that you need to achieve. Because when you have surface diffusion effects like this, what is the spatial resolution of the technique? I don't think anyone can tell. All right, just a few things to keep in mind for later. So Atom Probe relies on the time-controlled thermally assisted field evaporation to emit the ions from the specimen. The control can come from either using high voltage pulses to increase the fields temporarily, or laser pulses that increases the temperature. Typically, high voltage pulsing leads to more reliable data, more reproducible data, but suffers from a lower yield because the field being higher, the electrostatic pressure is higher, and this will tend to break specimens more easily. Laser pulsing is more gentle on the specimen. You can analyze a broader range of materials, but the performance can be harder to quantify, and there is more fluctuations from specimen to specimen. I must say that I tend to be a bit fed up with people telling me, oh, but I use the same analysis conditions than blah, 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 or than in this paper. And actually, it means nothing because if you take 40 picojoule as a laser pulse energy one day and use the same laser pulse energy the next day, the peak temperature that you're going to reach for two different specimens is not the same. So I hope this triggers some thoughts in your head, and if you end up having questions and want to discuss, I'd be happy to answer them or discuss with you. Thanks for your attention, and see you soon.